All right, so the new method that we talked about in this section was the trapezoidal rule, and we've been using it in comparison to the midpoint rule. And interestingly enough, even though when we looked at the trapezoid rule, it seemed like it would be a better approximation method, the midpoint rule has so far outperformed it. That's going to change with this last method that we talk about. So there's one more approximation method that we're going to deal with here. It's not the only other one that exists, but it's the only other one that we're going to talk about. It's something called Simpson's method. And we start in a similar way as all of the other approximation methods. We're looking at approximating the area under a curve, this blue curve here, over some interval a, b. And we start by chopping up that interval into n subintervals, all of equal width, which we call delta x. For Simpson's method to work, there's a condition we place on that. So we don't just get to chop this thing up into any number of subintervals. It has to be an even number for this to work. So you can cut it up into 2, 4, 6, 8 subintervals if you wish. You just can't cut it up into 7 or 11 or whatever. It has to be an even number of subintervals for Simpson's method. What we're going to do is take pairs, consecutive pairs of those subintervals, and kind of use them together. And then the endpoints of those, so for example, this first pair of subintervals are going to have the endpoints x0, x1, and x2. We're going to plug all three of those endpoints from that pair of subintervals into our function to determine points on our curve. And then that gives us a set of 3 points. So here in this first pair of intervals, I have P0, P1, P2, 3 points on the curve. And then my next pair right here, I have P2, P3, P4, 3 points on the curve. And then you can see where that continues. We're going to use the fact that for any 3 non-collinear points in the plane, there's a unique parabola that contains all 3 of those. So you can see that I have this red parabola right here. Or actually, I'm sorry, I think the... Oh, yeah, the red ones are the parabolas. I have this red parabola here. I have a red parabola here passing through P2, P3, P4, and then another red parabola right here. Oh, no, I'm sorry. The picture is making this kind of tricky. So the red one is the actual curve. The blue curves are the parabolas. But you can see where they pass through those points. We're going to use the area under those parabolas to approximate the area under the actual curve. We're going to expect this method to work a little bit better because this is the first approximation method where we're using actual curved graphs instead of straight line segments like in the trapezoidal rule or the midpoint rule. Because parabolas are curved, they can conform to the shape of an actual curved graph better than those rectangles or those trapezoids can. So in order to do this, we need to figure out how we would add up the areas under all of these parabolas. So in order to do that, let's consider kind of a simple case. Suppose we have a parabola that passes through these 3 points, P0, P1, and P2. And those 3 points are going to come from these 2 subintervals here, which together give me an interval that's centered about 0. So I have one subinterval that goes from negative h to 0, and then another one that goes from 0 to h. By centering it around 0, we're going to simplify the work that we need to do to figure out what this computation is going to look like. The next thing we're going to do is, because this is a parabola, we know that it comes from the graph of a quadratic function. So let's suppose that quadratic function is this: y equals ax squared plus bx plus c. To find the area under that parabola, what we're going to do is integrate from negative h to h, because that's where that area is accumulated. Now, I don't know what a, b, and c are, but I can do this integral just in terms of a, b, and c, and we're going to use some symmetry here. If I were to ignore the bx term and just do ax squared plus c, then that would give me an even function. And I know that if I integrate an even function over an interval that's symmetric about 0, like negative h to h, then I can change this to the integral from 0 to h instead of negative h to h and just double the result. Then when I look at this bx term, if I were to separate that out into its own integral, that's an odd function. And we know that when we integrate odd functions over intervals like this, it's always equal to 0. So that means that b to the x term is going to give me a 0, which doesn't contribute anything, and we can just get rid of it. So now I'm evaluating 2 times this integral right here. As a polynomial, that's easy to integrate. I would get a times x cubed over 3 plus cx from 0 to h. And don't forget that we have that 2 out there. Plugging a 0 in makes everything go to 0, so really I just need to plug an h in, which gives me this. And then I can simplify this a little bit by factoring, or by multiplying the 2 in and factoring a 1/3 out. Okay, so if I were to do all that, in fact, I'm going to do a little bit more. I'm going to factor an h over 3. Notice I have an h in each term. I'm going to pull that out. I'm going to pull a 1/3 out, multiply the 2 in. I get this expression right here, h over 3 times 2ah squared plus 6c. Okay, now this is the area under that curve, but we know a little bit more about this parabola. Specifically, we have 3 points on that parabola. So if I were to take those 3 points, treat them as an x and a y value that I could plug into my original equation up here, I'm going to get these here. So for example, if I plug negative h into this, I'm going to get a times negative h squared plus b times negative h plus c, which simplifies to this, and that should give me the y naught that I'm using as the y coordinate of that point. If I plug 0 into this, then the first 2 terms go to 0 and all I get is a c. So y1, the y coordinate of that point, is just equal to c. And then y2, I would plug an h in to get y2. So ah squared plus bh plus c equals y2. I'm going to think of these 3 equations as like a system of equations, and I'm going to manipulate them the way that I would do with a system. So for example, notice that if I were to add y0 and y2, that's this and this here, or that's like adding this expression to this expression. The bh and the negative bh are going to cancel each other out. And that's going to leave me with 2ah squared, because that's showing up twice. So there's where the 2ah squared is coming from. And then I'm going to have 2c as well. Now I don't see a 2c here, I see a 6c. So where's that coming from? Well, notice in this expression here, I'm also adding a plus 4y1, which is the same thing as 4c. So if I already have 2c here and I add another 4c, I'm going to have 6c here. And what was the purpose of doing that? Well, that 2ah squared plus 6c is exactly what we saw showing up here in the area formula for the area under that parabola. So that means I can replace the stuff in parentheses here with y0 plus 4y1 plus y2. Okay, that is now the area under this parabola in terms of these y coordinates now. Let's use that. Like this. Okay, so now I know that if I were to take that parabola and if I were to shift it around horizontally, then the area under it wouldn't change. So I can shift that to, instead of the original points, P0, P1, and P2, I can shift it to wherever the interval I actually want to integrate over is, and, you know, put it over those 2 consecutive subintervals where we're finding our parabola. So for example, if x is equal to x0, x1, and x2, right? So I would use that here. And I could then kind of use the same result over and over again for the other parabolas as well. So, you know, if I want to move on to my next subinterval, instead of having y0, y1, and y2, I would have y2, y3, and y4 as an example. And to see where that's coming from, this would be like y0, y1, y2. That covers this first parabola. y2 appears again, y3, y4. That's the next subinterval there. So we kind of do that for each of those parabolas. So that means that if I want to approximate the area under that curve using parabolas, which that's what we call Simpson's method, then each of these terms here, which with an h over 3 out front, represents the area under each one of those parabolas. So I'm summing those up. Okay, but then if we simplify this, notice I have an h over 3 showing up in each big term here, which can be factored out. And what's going to be left? I have a y0 plus 4y1 plus y2, but then here I'm going to have another y2 because that's where these two parabolas meet each other. So that y2 gets used twice. I can add that up and make it a 2y2 right there. And then I'm going to have 4y3, that appears there, then a y4 here. But in the next term that you're not seeing because it's got the dot, dot, dot here, there would be another y4, so I have 2y4. And this pattern is going to continue. So what we're seeing is a y0 and a yn. These are like the outer end points, kind of like with the trapezoidal rule. We don't multiply them by any coefficients. But then inside all of these remaining terms between those two, I'm multiplying them by either a 4 or a 2, and I'm alternating. So 4, 2, 4, 2, 4, 2, 4, 2, all the way through to this second to last term right here. Those y values we get by plugging in the corresponding x values for our function f. So Simpson's rule would be actually written this way. Now the h that we saw in these expressions here, if you think about where that came from, remember that these are two consecutive subintervals. So if I look at just one of them, h would be the width of that subinterval. In our approximation methods, we tend to call that delta x instead of h. So that would actually look like a delta x over 3. And then here's all those terms that we saw. Okay, so let's use Simpson's rule in an actual example. We're going to use it with the same integral we've been working with this whole time. I'm going to use n equals 10. I can't use n equals 5 like I did in the previous examples because for Simpson's rule to work, you need to have an even number for n. And again, that's because we treat those subintervals in pairs. So you can't pair up an odd number of things. So for Simpson's rule, we're using this approximation right here. S10, S for Simpson's, that's the notation we're going to use. That's equal to delta x. We already computed delta x before. It was 0. Oh, I'm sorry, delta x is actually different this time. 2 minus 1 over 10 now. It's not over 5 anymore because we have a different value of n. This is 0.1. So delta x is 0.1 over 3. And then we have f of x1. Now, what are my subintervals going to look like? Remember, we're on the interval from 1 to 2, and we're dividing it up into subintervals of width 0.1. So that means I'm going to end up with 1, 0.1, 0.1, 0.2, and you can kind of see the pattern here. We're going to end at 0.9. Oh, I'm sorry, these should be 1s. 1.1, 1.1, 1.2, 1.9, ending at 2. Okay, so my first endpoint is just 1. F of 1 looks like 1 over 1. Then I have 4 times f of 1.1. So that's plus 4 over 1.1 for this function. Then we add 2. That's the next thing. Remember, alternating 2s and 4s over the next endpoint, 1.2 plus 4 over the next endpoint, 1.3. And you can see a pattern here. So I would have to write all of this out if I'm putting it all into a calculator, but I can kind of do this dot, dot, dot here to indicate the pattern. Notice the 4s appear in the numerators where I have an odd digit in my 10th place. So if I'm trying to go all the way out to say like where my denominator is 1.9, I know that that would be a 4 there. And then finally I'm going to have plus 1 over 2. That's the last endpoint plugged into my function there. So this all is going to go into a calculator, and what I end up with in this example is 0.969350, which if you compare to what we know the actual value of this integral to be, it's a significantly better approximation than what we got with our other techniques. Okay? So like with the trapezoidal rule and the midpoint rule, Simpson's rule also has an error bound. We can't prove this one because it requires more advanced math, just like the other error bounds, but we are going to use it. Notice for this one, it kind of looks similar to what we saw previously, but there's some important differences. So there's that k appearing in the error bound, and that k comes from the the absolute value of our fourth derivative of our function. It's not the second derivative anymore, it's the fourth derivative. So we'll need to take more derivatives and then find an upper bound for the absolute value of that on the interval a, b. For our example, it's going to be the interval 1, 2. And then the error bound is k times b minus a to the fifth power now, so larger exponent, over 180 n to the fourth. This is a significantly larger denominator than we saw for our error bounds for the trapezoidal rule and the midpoint rule, which means we're going to get a much, much smaller error than we were seeing in those examples for the same value of n. Okay, so to wrap things up, we're going to do a similar type of question that we've already seen, but applied to Simpson's rule. We want to figure out how large n has to be in Simpson's rule to ensure that our approximation to this definite integral is accurate to within 0.0001. Same idea as before, but we want to see what the size of n has to be when we use Simpson's rule. So again, what we're doing is we're using this error bound right here. So I want to keep this quantity less than or equal to 0.0001. And in order to do that, the error bound for Simpson's rule said that we needed the fourth derivative of our function. So f of x is equal to 1 over x, f prime is negative 1 over x squared, f double prime is going to be equal to 2 over x cubed, f triple prime is equal to negative 6 over x to the fourth, and then finally our fourth derivative, the one that we want, is equal to 24 over x to the fifth. Okay, now the absolute value of that, we want to make it as, or we want to see what the absolute largest it could possibly be is. That's the value of k that we're going to find. Remember that we're looking at the interval from 1 to 2, and also the larger this denominator is, the smaller the quotient is, and vice versa. The smaller that denominator, the larger this gets. So to make it as large as possible, I want to use the smallest value of x from this interval, which is 1. So it's less than or equal to the absolute value of 24 over 1 to the fifth power, which is just 24. Okay, so that's going to be the k in our example. So now Simpson's rule said that we had k, which was 24, times b minus a, or 2 minus 1 to the fifth power, over 180 times n to the fourth. And we want to keep that less than 0.0001. I could also say less than or equal to, but it's I'm going to get the same answer either way. Simplifying things a little bit. So I'm solving for n. So if I multiply both sides by 180 n to the fourth, divide both sides by 0.0001, I'm going to get 24. I already know that this part is going to be equal to 1 over 0.0001, like that. Then I'm going to divide both sides by 180, so I get 24 over 180, 0.0001. It's less than or equal to n to the fourth. Then I need to take a fourth root of both sides. Like that, less than or equal to n. This is where you plug things into a calculator. I'm going to switch things around a little bit. This time, if I plug this in, I'm going to get n is greater than or equal to approximately 6.04. So we need n to be larger than this because this is not an integer. We need a whole number. Oops, I went off the screen. We need a whole number here. So the next whole number is 7, but I can't use 7 because Simpson's rule requires even numbers. So really the next best value for n would be 8. Okay, so for comparison, when we used the midpoint rule, we needed about 29 or 30 for n to get the same level of accuracy, when we use the trapezoidal rule, we needed 41 for n. And remember, the larger n is, the more computation you have to do. Simpson's rule only requires n to be equal to 8 to get that same level of accuracy. So what that's saying is that Simpson's rule is way, way more effective at getting us good approximations with minimal amount of computation involved. Okay, so that's going to wrap things up for 7.7.